It's going to be first. So today we're going to finish up talking about our membrane potentials. We're going to go over a new concept called the equilibrium potential. We're going to finish up thinking about our electrochemical driving force. Just a reminder where we left off, okay? So we're talking about how and why we have things move in and out of the cell. So between the intracellular fluid, the ICF, and the extracellular fluid, the ECF. So from before, hopefully we know that we have a chemical driving force, a CDF, and this is due to the chemical concentration of whatever molecule ion we're looking at. I should note here, when you're looking at chemical driving forces, you're specific about that specific molecule or ion. So when you're looking at the chemical driving force on sodium, you're thinking only about sodium ions. You're looking at potassium, you're thinking only about potassium ions. You're thinking about glucose, you're thinking only about glucose. I'm saying that because that's different than when we look at our electrical driving force. So our chemical driving force, we're looking at concentration, and we're going to go from high concentration to low concentration. That's always the direction for our chemical driving force. So high, low, could be into the cell, could be out of the cell, just depends on where you have that high versus low concentration. That's our question. For our electrical driving force, our EDF, what we're interested in are charges. So for our electrical driving force, we need to know the charge inside the cell, and we need to know the charge on our ion. We're only going to be looking at the EDF if we are talking about an ion, because that's what has a charge on it. So we need to know sodium positive, we need to know chloride ions negative, and we need to know whether our membrane potential of the cell is positive or negative. So when I said that we care about only sodium when we're thinking about, for example, the chemical driving force, but it's a little different with the electrical driving force. I said that because when we think about the membrane potential, so the membrane potential, BM, okay, membrane potential of our normal cell at rest, negative 70 millivolts. Okay. So that negative 70 number, that doesn't come from just sodium, which, right, sodium is a positive ion. So it makes sense that you must be accounting for things other than sodium to get that number. Okay. So when we figure out that membrane potential, we'd be counting up all the sodium, all the chloride, all the potassium, all the calcium, all the ions to get that charge difference across the membrane. So that membrane potential takes into account everything. So when we're looking to find the direction of our electrical driving force, we're looking at the charge on our cell. Sodium is an example again, because we talk about sodium throughout this course. We're looking for that charge on the cell. We're looking for valence on our ions, a little charge on that. So sodium is a positive ion. This cell is negative inside. So our opposite charges attract each other, like charges repel each other. So here we have a positive ion we're interested in, and we have a negative cell. Our EDF would point in towards the inside of the cell, towards our cells. So those are the things we're considering when we're thinking about these two forces separately, the CDF and the EDF. And then when we think about the ECDF, so electrochemical driving force, squishing together these two words, ECDF. Okay. We're just combining these two forces. So if they're in the same direction, we add them together. If they're in opposite directions, we're going to end up subtracting the smaller one from the larger one. Or you can think of it as adding a negative or being in the opposite direction. Either way that makes sense to you to think about it, both are going to get you to the same result. So we just add our CDF plus our EDF in the same direction. And that would give us our total force here, our total electrochemical driving force on sodium. So this is where we hopefully all are up until this point. Questions about these three pieces? So now we're going to talk about the equilibrium potential. Equilibrium potential is a membrane potential, but it's a type of membrane potential that's going to be specific to a specific ion. You can think of it as kind of like the membrane potential that that ion wants to get the cell to. Okay. So this means when we are at the equilibrium potential for a given ion, we're going to cease movement of that ion because it's where it wants to be. And when we have no movement happening across that membrane, that is because our chemical driving force and our electrical driving force are equal and in opposition to each other, so in opposite directions. So looking at this example, so what we can see on here, readily this. Okay, so we're starting out with a membrane potential at negative 94 millivolts. So VM, we already know what that means. Okay. But we have a new label on here, right? So we now have this EK, okay? E sub K. So the E is for equilibrium. So E for equilibrium. And the K is telling us that this is about potassium. So K is our symbol for potassium ions. So this would be saying the equilibrium potential of potassium equals negative 94 millivolts. So this means if our cell is at negative 94 millivolts, so if VM, our membrane potential, equals EK, our equilibrium potential for potassium, that means that there's no overall force for potassium to move. So we can see that drawn out here. So when our cell is at negative 94 millivolts, we have an electrical driving force on potassium, so an EDF, that points in, because potassium is a positive ion, and the inside of our cell is negative, right? Okay, so that's our EDF. And at the same time, we have a chemical driving force that points out. This chemical driving force is because when we're looking at the concentration of potassium, specifically potassium, we can see we have a high to low gradient. So we have high potassium inside the cell to low potassium outside the cell. High to low, our CDF points out. So these arrows are drawn same length, same size, because we are at the equilibrium potential. They're fighting each other perfectly so that we can end up with zero movement, despite the fact that there is a chemical concentration gradient across this membrane. This electrical driving force is preventing potassium from moving along that gradient. That's the fundamental idea of our equilibrium potential. So we're always going to have an E for equilibrium potential Here where it says X, that's a variable just standing in for whatever ion we're talking about. So in the picture, it's EK, so equilibrium potential of potassium. It could say ENA, equilibrium potential of sodium, ECA, equilibrium potential of calcium, and so on. Okay. So if we look at our membrane potential as it exists, so what the cell is at, and we compare it to our equilibrium potential for that ion, and they're the same, our electrochemical driving force, our ECDF, will be 0 because we have opposite chemical driving force. We can think about this as one potential being stronger than the other. Okay. So I'm hesitating a little bit because I don't actually think that this is the simplest way to do it. But you'll note here, we're looking at a membrane potential in B here of -70 millivolts. And we can see that this equilibrium potential of potassium is stronger, so larger, or sorry, yeah, is larger than that. So we might say the membrane potential Vm is weaker than the equilibrium potential of potassium, EK. So we can see that this chemical driving force therefore predominates and drives that electrochemical driving force. So if Vm is weaker than E of whatever it is, the chemical driving force wins. If Vm is stronger, so that membrane potential is stronger, in this case -100, is bigger magnitude than -94, then we have our electrical driving force predominating. Okay. So if that makes sense to you, think about it that way. I said I don't think this is the simplest way to do it. I don't. So the way I do it in my head is I compare our number for the equilibrium potential to that number for the membrane potential. And I just think, what direction would potassium need to move to get to -94 for the inside of the cell? So do I have to move that positive charge into the cell or out of the cell to get to my -94? So since potassium is a positive ion, we're at -70, want to get -94. We need to make the inside of the cell more negative. One way we could do that is by taking this positive ion out of the cell. As we do that, we get more and more negative towards that equilibrium potential. And that's the direction of the electrochemical driving force in this situation. It works for the other example as well. So if we are at a membrane potential of -94, but the equilibrium potential of potassium tells us we want to be at -94. So we want to be a little more positive than our starting point, than Vm. We want to be more positive. We're thinking about this positive ion potassium. The way we make the inside of the cell more positive is we take our positive ion and move it. That also gives us the electrochemical driving force. I think this is a little easier because I only have to think about the one thing, but your mileage may vary. So regardless, we're trying to get to a point for that ion where our equilibrium potential is the same as the membrane potential, which means our two forces, chemical and electrical driving forces, are equal and in opposition. So this can be for you to practice later. These are checkpoint questions from the book. Gives you concentrations of solutes that are in a typical cell in the intracellular fluid versus in the extracellular fluid so surrounding. So you want to be able to go through and think about concentration gradients, think about what that means about the CDF here, and then we tack on electrical driving forces and add them together for the electrochemical force. Let's do a practice example. Okay. I'm going to tell you here that sodium has an equilibrium potential of +60. We're going to start with a cell that is at our usual resting membrane potential of -70. I want you to tell me, to predict what direction our electrochemical driving force, our ECDF, would be on this cell. Start drawing and labeling our cell. You guys finish that up and then we'll walk through it together. Tells us that we're starting at our membrane potential of -70 millivolts, typical resting membrane potential for a cell. Okay, and we're thinking about sodium, a positive ion. So we can think about all sorts of forces just from this information. The review will actually start with our electrical driving force, our EGF. So we know the inside of the cell is -70. Sodium, the positive ion, positive and negative attract. Right, so sodium, our EDF points in. That's our electrical driving force, just based on those charges. We're actually looking for our electrochemical driving force, which is the which is the overall direction sodium wants to go. Also has to take into account that chemical driving force. So we want to make sure that we understand all the pieces going on. We don't, in this example, have information about our concentrations of sodium directly, but what we do have is our equilibrium potential for sodium. So we know that once we get to this point, the CDF would point in the opposite direction to our DF. The way I like to think about this to figure out our ECDF I just think about how we would get from -70 millivolts to +60 millivolts. So to go from this negative number, make it more and more and more and more and more positive. Our sodium would have to go in because it's a positive ion. So our electrochemical driving force on sodium is into the cell from this membrane potential of -70. Is the case that to get to that positive 60, we had to cross 0. So once we cross 0, the positive, our EDF would have flipped with the CDF continuing to drive in. So it's a step farther than, it's a step farther than I'd expect you to right now at the beginning of this concept be able to do, but we can also actually figure out from this information that our chemical driving force points in as well. We'll do another example here. So for this example, we're going to look at a chloride ion. Okay. We're going to try and figure out whether it moves into or out of the cell. So when we're trying to figure out which way it will actually move, that means it's a question about our electrochemical driving force, so long as we're talking about an ion, it's a charge. So to do this, we're thinking about comparing our membrane potential that we're starting at, -66. We're comparing to our equilibrium potential for chloride ions is -61. We also have a chemical gradient drawn on here as well. So for those chloride ions, we have concentration of 60 millimoles outside, 6 millimoles. Things we might want to be able to answer about the cell overall. We're thinking about our driving forces. We know that those concentrations could tell us about the chemical driving force, but we're interested in our total net movement. So we're interested in the electrochemical driving force. So we're going to just do that bit first. So for electrochemical driving force, we take that -66. We know we have a negative ion. We want to get to -61 inside the cell. So overall, we are going to have to move chloride ions out. So this tells us, right, if we remove a negative charge, that number is going to get more positive. So we go from -66 to -65 to -64 and so on until we get to -61. By moving those chloride ions out. But while we're looking here, we can practice looking at our CDF and our EDF as well. So for our CDF, chemical driving force, looking at those concentrations, we know we go from high to low into the cell. But what's predominating here, what's taking control, is that electrical driving force. So our EDF, we know chloride ions are negative. Right? Chloride ions are negative. The inside of the cell is currently negative. Like charges repel each other. So that negative is what's pushing those chloride ions out. And that's going to be stronger than this chemical driving force moving in, which is why in total we have this. Kind of how all these things sort of play together, these multiple forces. Okay. Yeah, let's do one more example. Not a warm up, but be a practice. So let's try a cell where we have membrane potential of -70. I'm going to tell you that the electrochemical driving force for potassium, A+ points out. I want you to think about what the electrical driving force on potassium is, what the chemical force on potassium is, and which force is going to be stronger. We're looking at problems about the electrochemical driving force, and the chemical driving force and electrical driving force. They can be asked in a variety of different ways, so they can sometimes seem kind of tricky. What I really recommend you doing, if you're a little bit sort of going blank when you see the question, is just start drawing it out and put on anything you do know about the situation, then you can figure out. And eventually it will all kind of build up together. So you don't have to attack a whole question at once. First, just put on what you do know and then reread the question, and that should probably help you out. Okay. In this case, sort of stepping you through how I might think about some of these situations. So we're looking at a cell at our resting membrane potential of -70. We actually already know that the ECDF points out, because that's given to us in our example. Okay. So to find the electrical driving force, our electrical driving force, has to do with like charges repelling, opposite charges attracting. So all we have to do for point A is to think about those charges. So we're seeing that our cell is at -70, potassium is positive, so our electrical driving force is attracting our potassium. So our EDF, just based on those two things, what's in. Figure out the chemical driving force without having concentration information. What we could do here, we see that our electrical driving force is pointing in, but our electrochemical driving force is pointing out. Okay. If the EDF and the CDF were in the same direction, the electrochemical driving force would be pointing in as well. So we know that the chemical driving force has to be pointing out. And in fact, we know that it has to be stronger than the EDF because we're just adding and subtracting things. In this case, our chemical driving force points out, and it's the stronger one in this situation. Questions about these three forces, how they go together, or overall the equilibrium potential? Try to do some more practicing before we get to our next week, but October 2nd, so I think that might be next week if I remember how dates go. Yeah, so we'll practice this more. just so that you know, this is one of the concepts that you do want to make sure you really have down by the time we get to the exam. I know a lot of the other stuff in this unit should be reviewed from previous courses, but this electrochemical driving force here is new for everybody. So sometimes it can kind of trip you up if you don't think about it long enough. So next we're going to be talking about transport. So hopefully this is going back to some material that you have seen before. So when we're thinking about transport, we're thinking about movement across the membrane. Thinking about movement across the membrane, we're going to have movement under normal situations where we don't put any energy in, until the point we reach equilibrium. So we want equal concentrations on either side of our membrane. Otherwise, we are going to have essentially a force. We're thinking about ions. We now know that we also have to add on our concept of the electrical driving force that plays a little bit of a role in here. But diffusional equilibrium is reached when we have no net transfer of molecules. So equilibrium means nothing's moving on it. Might be jiggling around a little, if you added up everything, no movement. So we're going to think about a number of different types of transport, but we can first break them into essentially two classes. So passive transport versus active transport. The passive transport, we are going to be moving in the direction that that molecule or ion wants to go. So for glucose, which doesn't have a charge on it, we'd just be following our chemical concentration, that chemical gradient going from high to low. If we were thinking about an ion, we're going to think of passive transport as being in the same direction as the electrochemical driving force. So to go with that force doesn't require any energy. So passive transport is going to be spontaneous. It happens on its own. The cell doesn't have to put in any energy. We can think of it as moving downhill, down gradients with the driving force. It doesn't have to fight against anything. Okay. That's in contrast to active transport, where you're going to have to put in energy at some point in some form. But before we do that, we want to mention that there are different types of passive transport. Okay. So passive transport is always going to be in the direction that the molecule wants to go, but how it gets there is what differentiates our three types of passive transport. We're going to have simple diffusion, facilitated diffusion, and diffusion through channels. We're starting with simple diffusion. We're thinking about our cell, our plasma membrane. We're thinking about its composition when we think about simple diffusion. So we know that that membrane is mostly made up of our phospholipids. Okay? And they're sitting end-to-end, polar hydrophilic heads on the inside and outside. This double layer of fatty acid tails on the inside of the membrane. Cool. All right. And we know that membranes are selectively permeable, so only certain things can get across. I'm not going to draw all the phospholipids because I'm slow, but that's what's in this structure of the membrane. Okay. So in simple diffusion, we don't need any membrane proteins to be present because we're going to be thinking about things that can just go straight through the lipid bilayer. So when we think about simple diffusion, we're thinking about things that are small enough to squeeze between our phospholipids, and they're non-polar because they have to cross this non-polar region with these hydrophobic fatty acid tails. So this is going to be things like oxygen. Small non-polar gases are the most important thing that moves by simple diffusion, I would say. There are some different factors that are going to influence how fast something can diffuse across the membrane. So one of these things is the magnitude of the driving force. So if we have a bigger force, for example, if we're thinking oxygen, no charge, so we only have to think about a chemical driving force. Big force would be caused by like a big gradient, lots and lots and lots of oxygen on one side of the membrane, only a tiny bit on the other side. The magnitude of the driving force would be bigger. Membrane surface area, so how big that membrane is, actually does make a difference, because for simple diffusion, you're kind of waiting for that oxygen to swim around and touch the membrane to go through. Okay, so that's what's happening, which means that if you have more surface area, more membrane, you're more likely to hit the membrane and move through. So greater surface area means faster diffusion, and get into that cell faster. The other thing that we might add on to this, if we're thinking about the rate, even though for simple diffusion, we want to think about something that can definitely get through this lipid bilayer, the membrane could be more or less permeable. It doesn't mean that everything is going to get across quite as easily as everything else. If the membrane is more or less permeable to that substance, that's going to make a difference for the rate. If it's more permeable, more gets across faster. Essentially, each of these factors would speed up the rate. Greater driving force, greater diffusion, more surface area, more diffusion, greater permeability, also more diffusion. So here we can see concentration gradient going up and up and up. Right? So I see a graph, greater concentration gradient. So this is a delta, that's a triangle's delta. So that's a difference. So difference between the concentration inside and out. So as it goes up, net flux. Flux is movement. Net means total. So the total movement goes up as the concentration gradient goes up. Here we see some membrane surface area. Greater membrane surface area, so more space, more walls essentially to go across, greater likelihood of bumping into one of those walls is going to speed up the diffusion. And our permeability also has an effect. So if something has low permeability, if the membrane only has a little bit of permeability to some molecule, we'll see the net flux, so the overall movement, the overall simple diffusion will go up over time with this concentration gradient, but it's not going to go up nearly as fast as if that membrane is highly permeable to that substance. So that membrane permeability could have to do with the lipid solubility of the diffusing substance. So if something can diffuse easier, it's more lipid soluble, then it's going to go across faster. If it's a little bit lipid soluble, low permeability, going to go slower. So certain vitamins or medications, you will eventually learn are lipid soluble. It's not always just oxygen. Size and shape can make a difference. It needs to be small enough to diffuse across the membrane in the first place, but some things are a little bigger, some are a little smaller, some things different shape. Temperature would make a difference in that if temperature goes up, stuff moves faster and therefore diffuse faster, but temperature is a regulated variable, part of homeostasis in human bodies. So that's not going to be really relevant for human physiology, which is what we're concerned about in this course. Thickness of the membrane also makes a difference. So if we're expanding beyond just cell membranes, a thicker membrane, if you have something collecting and blocking kind of one side of the membrane, that would actually slow stuff down because there's just more of a to cross. And just practice questions. We'll move on to facilitated diffusion. The facilitated diffusion is still passive transport. So it's still going in the direction that we want to go, and we don't have to put in energy. But now we're talking about something that can't get across the lipid bilayer on its own. So it's something that's too big or it's not lipid soluble, right? So something polar or something with a charge on it. So in facilitated diffusion, we're going to need membranes. Sorry, we're going to need membrane proteins because we can't go directly through the phospholipids. So in this case, we have an example of glucose and a carrier protein. Okay? So this protein is an integral transmembrane protein, goes all the way across, and it's a glucose carrier. So what happens is it has a binding site, so a little slot for glucose to come in on one side. And then that protein flips around, slot flips around. Now glucose is on the opposite side of the membrane and can be released into the ICM, into the intracellular. At the end, that transmembrane protein is going to go back to its original state, waiting for glucose again. So we can reuse these transmembrane proteins for transport. So a carrier catches our molecule, moves it to the other side, but we didn't use any ATP here, we didn't use energy. The movement is all just based on chemical properties. We talked about proteins folding in those different ways based on hydrogen bonding and their R groups and their subunits. So basically our molecule binding in changed something about that, which changed the shape of the protein. It's not because we put in energy. So this is still passive. So we can think about the rate of transport here. So we're still going to see that the rate of transport speeds up as we have our concentration gradient increase. So this force is getting bigger as we have a greater difference in concentration inside versus outside. So our flux, our net movement goes up over time. But at a certain point here, we're going to see a plateau. So when we were looking at simple diffusion, we just had a straight line going up and up and up and up forever. If we're thinking about facilitated diffusion, there's a point at which we hit essentially a maximum rate of facilitated diffusion. So this has to do with a couple things. Mainly has to do with properties of that carrier protein. So one thing that is true is that each of those carrier proteins has a rate of transport. So you can think about like a time scale on how long it takes for it to flip across. Right? How long does it take for it to change shape and move glucose to the other side of the membrane? So that's going to slow things down a little, depending on the rate. The number of carriers in the membrane is also going to make a huge difference, because eventually we're going to reach a point at which all our proteins are full, right? We're going to have a saturation point where even if our glucose comes up to that cell, there just aren't any carriers for it to go through, which is the really big factor on this flattening out. So an example of a type of facilitated diffusion is glucose transport through glucose transporter 4. So the GLUT4 molecule is something that's made in our rough endoplasmic reticulum. Okay. This transporter gets packaged into vesicles, so little baggies inside the cell. And in the presence of insulin, so insulin is going to be a hormone that we'll talk about in our endocrine system. When insulin is present, those little vesicles merge into the membrane. Essentially, we end up with lots of extra GLUT4 transporters in that cell membrane. Okay. This means, go to example cells. Okay, so before presence with insulin, let's say we have like one transporter here. And then after insulin is present, we took a bunch of transporters that we just made. They were in vesicles. And now we have more transporters in the membrane. Okay. So that's what happened in the presence of insulin. So that's what this bit means. Okay. So this is a factor in a certain type of diabetes. So in diabetes, because the insulin action isn't working, This means that we don't insert as many of these transporters into the membrane. And that's a problem because the point of this transporter is to let glucose into the cell, right? So before we have insulin present, in this example, we get 1 glucose in per unit of time. Insulin present, inserted a bunch of transporters. Now we get in 3 glucose molecules per unit of time, which means we're able to drop that blood sugar faster because we're pulling glucose into the cell. In diabetes, and you can't do this, that glucose essentially gets stuck floating around in the blood because the cells can't pull it in as fast. So this is what would raise the blood sugar after eating with this lack of insulin function. Final type of passive transport that we want to know about is diffusion through channels. So channel is also a transmembrane protein, just like our carriers were. So it goes all the way through. So here's a channel protein. And it functions essentially like a pore. It's just this hallway that we can have something go through. It will be substance specific as well. So we will have sodium channels, we'll have potassium channels, so on and so forth. Passive transport. So sodium, there's this open sodium channel, would follow its electrochemical driving force through that channel. There's some types of channels that exist, and this is where we will end today. So we have aquaporins, are channels for water. So we mentioned that unless I tell you otherwise, we're always going to think about a cell as having aquaporins. So we're thinking of water being able to cross, but it is because of a channel protein. We have lots of ion channels that we will think about throughout this course. So we're going to have leak channels that allow a little bit of ions to leak through. We're going to have gated channels. So when they're open, they act just like a pore. They don't have to flip across like a carrier protein, but they are going to have a gate that we can shut close, so they're not always going to be open. We'll have some channels that work in 2 directions, so stuff can go in, stuff can go out bidirectionally. These are just like the carriers, going to have a transport rate. How fast stuff gets across. That rate of transport is going to depend on how many channels we have open. And it's going to depend on whether those channels are open or closed, since they may have 2 states. Okay, that's where we'll leave off for today.